Dear friends and colleagues, I wish you all very welcome to this webinar on the incorporation of risk and uncertainty in design and operations of water resource recovery facilities. The webinar will be something like 75 minutes, depending a little bit on how much questions appear towards the end. It is a webinar series that is an effort of the IWA specialist group on modeling and integrated assessment, what we normally call MIA. And we have them to highlight various aspects related to modeling. And this is the 12th webinar that we provide. My name is Ulf Jeppsson. I'm from Lund University in Sweden, and have the privilege of being the chair of the specialist group on modeling and integrated assessment. And before we start the actual webinar, I want to just take this opportunity to say a few words related to the work of the MIA specialist group. We try to be one of the most active specialist groups within IWA, and we are the group that are really focusing on modeling of every different aspect of water and wastewater processes and everything related to that topic. It is a specialist group that is open for everybody who's a member of IWA, and we currently have some 1,900 members. One of the most important ways that we work in the specialist group is through task groups. A task group is normally a small group of experts who is focusing on specific topics for a number of years, and normally towards the end produce an IWA scientific and technical report. And you see here we have four task groups that have finished, two of them very recent this year. Actually, this webinar is related to the task group on design and operation uncertainty. Then we have one task group who is almost finished, where the scientific and technical report is actually in press, and two task groups who are still very active. We also are active through working groups, and working groups is normally a somewhat larger group of persons that are promoting and investigating a more general topic. And you see that we have 3 different working groups within the specialist group at this time. And thirdly, we also reach out through our 2 main recurrent international conferences, the WRR Mod and the Watermatics Conference. And speaking of conferences, our next main event is the WRR Mod 2023, or it's also called 2022 Plus, because it was originally supposed to take place in 2022. And that modeling seminar will take place in Stellenbosch in South Africa in January 15 to 18. And it will be organized by Dr. David Ikumi and his colleagues in South Africa. Then in the late summer of 2023, we have the Watermatics 2023 Modeling Symposium in Quebec City in Canada. And that will be organized by Professor Peter van Rollegem and Dr. Elena Torfs. Peter van Rollegem, who's actually one of the speakers today as well. And we also most likely have the final location for the WRR Mod 2024 already defined. If everything works out, it will take place in Stove in Vermont in the US. If there is nobody who knows about the work that we are doing within MIA, then we hardly exist. Therefore, we have a number of communication channels sorry, for you and others who want to learn more about our activities and follow news and updates. We have the official MIA website at IWA Connect for all IWA members. But if you're not a member of IWA, you can still find almost the same information at our open website, which you see here on the screen. Then we also have LinkedIn and Twitter, and we also produce a regular newsletter that is sent out to all members. And finally, we have our own YouTube channel where we make webinars like this one generally available. So I just hope to see all of you as members of the MIA Specialist Group as soon as possible, if you're not already a member. Then just a reminder that we're also organizing a general open group MIA meeting during the IWA World Water Congress in September in Copenhagen in Denmark. There we can meet live and discuss and talk about topics that MIA is working on. Just before we start, just a few housekeeping rules. As you have already noted, this session is being recorded and it will go on YouTube in a few days. For all attendees at the webinar, your microphones and cameras cannot be used. Also, the normal chat function, you cannot use that one. Instead, every question that you have, please put it in your Q&A window that you open if you just press the Q&A icon. Put all your questions in there, and we will try to respond to your questions either in writing or orally during the Q&A session towards the end, as well as we can. And with that, I'm leaving the floor to the 5 different speakers that we will have, and ask Lina to take the floor and continue the webinar.
Thank you, Ulf. I hope you can all see my screen in presentation mode.
We cannot see your presentation at all now, Lina.
You cannot see my presentation at all. Okay, let's try it again. It seems that Zoom has locked me out.
Do you want me to use the slides, Lina?
Yes, why don't you start by starting the slides. Okay, let me also make the screen a little bit better, a bit bigger. Perfect, thank you, Wolf. Maybe I can try one more time if that's okay.
Okay, I can stop.
Just give me one more time. Can you actually see my screen now?
Nope.
How about now?
Now, Lina, now you're on.
And am I on presentation mode now?
Yes, please.
Perfect. Perfect. It seemed that Zoom had temporarily kicked me a little bit out. Okay, finally. Well, good morning, everybody, and good afternoon and good evening. My name is Lina Belja. I am the principal and co-founder of Primodal. I have about 30 years experience in modeling and operation of wastewater treatment plants. And I'm also the chair of the Design and Operations Uncertainty Task Group, or we call it DOUT for short. As Wolf mentioned, we have 5 speakers today. I will start by giving you an introduction to the Design and Operations Task Group, and I will also present some of the key topics discussed in the scientific and technical report we published last year. Lorenzo Benedetti will follow. He will introduce the basic concepts of uncertainty analysis, and then we will present some case studies. Bruce Johnson will start with an example of the use of uncertainty analysis using steady-state modeling, and Peter van Rollingen will follow with a case study using dynamic modeling. Last presenter is Mark Neumann, and he will give us some general perspectives on the work of the task group. And then we will have this Q&A discussion that Ulf mentioned. The task group was formed in 2008. It is composed of a core group responsible for the preparation and the editing of the scientific and technical report. And you can see the photos of the 7 members of the core group, the way we looked way back then. And we look slightly different today. The task group was also included a working group who contributed much of the material of the report, and you can see them listed on the right-hand side of your screen. So let me give you a little background on the motivation behind the formation of DOUT. So in my figure here on the slide, the figure depicts the established approach for water resource recovery facility infrastructure design. It involves, the use of design guidelines comprised of design rules, influent characteristics, operational targets, and other constraints are inputs to these equations included in the guidelines, and the tank sizes of a particular treatment plant are outputs. Risk is taken into account through the use of safety factors and peaking factors. And in general, we find that we end up with 2 engineering approaches. One would be a critical states engineering, so essentially based on worst case analysis. So for example, you think about the blowers designed on a maximum hourly airflow demand, potentially combined with a safety factor. And the second engineering approach is what can be described as a best effort engineering, and this is based on the analysis of the average conditions. So for example, the size of an aeration tank, sized on a daily average load, let's say. Now, there are several drawbacks associated with this established procedure. It mainly implies that we work in a well-defined and stationary environment, so it kind of ignores plant dynamics. If you notice in the slide, a single input gives you kind of a single output. It may also result in inflexible or inefficient designs. And this is because mainly it lumps risk in very few parameters, and it does assume a combination of worst case conditions that may never happen. It also does not provide us in a quantifiable way the likelihood that a design will actually meet an effluent permit, and it does not also address newly developed processes. So over the last decades, we are transitioning to using process modeling and data-driven methods in our design. And in operations also, I think we use more and more models for optimization, design of control. However, when we incorporate these models in our design procedures, which can actually overcome some of the downsides I mentioned earlier. In contrast to design guidelines, where uncertainty is accounted through the use of safety factors, in our models, we don't actually incorporate a formal risk evaluation procedure. So to include the evaluation of risk in model-based design and operations, models need to be combined with statistical methods. So these methods allow us to assign not just one, but rather a range of possible values to our inputs. So we capture the variability and uncertainty inherent in these inputs. So this allows us to assign appropriate level of uncertainty and make the risk of complying to effluent standards explicit. This is an overview of the contents of our scientific and technical report. It discusses the approach that I kind of mentioned earlier. The report is divided into 4 sections. The first section covers the key concepts of uncertainty analysis and a discussion of current practices and role models. Section 2 consists of a critical review of the methods that have been used in the wastewater field so far, and Section 3 presents the uncertainty analysis framework that we developed in the task group, as well as some case studies. The last section looks at risk and uncertainty in engineering projects in a broader view, And it also includes a chapter on the future directions of uncertainty analysis in our field. So in the next few slides, I will just give you a flavor of what is included in sections 3 and 4. So one of the major challenges in transitioning from the guideline/safety factor design approach to a more probabilistic based and model based design approach that we identified was that traditionally risk allocation often focuses on very, very few design or model parameters, and it tended to be done in a very ad hoc manner. So in order for us to create a more structured framework for uncertainty analysis, we compiled and categorized the most important sources of uncertainty that impact a wastewater project. And we developed an uncertainty matrix. So even though the list that you will find in the STR is not exhaustive, I think it covers most of the sources of uncertainty of interest. The slide that you see here, in the table in the slide, includes an abbreviated uncertainty matrix. In the STR, of course, you will find more details for each category or location, as we call it. And we felt that this classification would actually aid engineers in looking to pinpoint the sources of uncertainty in their projects, but also maybe help the transition of safety factors found in design guidelines to sources of uncertainty in our models. Another topic that was discussed in the STR is the fact that the relevance of each of these sources of uncertainty that I just mentioned earlier, that we include in the uncertainty matrix, it changes depending on the engineering project phase. So decision taking at different project phases will impact the final process design. If you see on the left-hand side figure, we have the little sketch that shows the different phases, starting from conception or planning all the way to a startup and operation of a treatment plant. And so, for example, if you think about it, during conceptual design, if an engineer might consider, let's say, a hydrolysis rate as being very, very uncertain, well, then that might result in a decision on the size of an aerobic tank, and this will actually follow the design all the way through. And of course, it will be different if a decision is made at a later stage. It will have a different impact. Another topic that we highlight in the STR, it includes discussing which uncertainty-related tasks need to be considered at each stage of a wastewater treatment modeling project, if we want to include uncertainty and variability. So, of course, we can use modeling in any of a project phase, an engineering project phase. So the right-hand side figure shows you the typical 6-step simulation-based project execution flow sheet. And we also have the uncertainty-related tasks marked, identifying, for example, that at the project definition stage is where we suggest that we select and prioritize some of the sources of uncertainty to be evaluated. The main part of the work of the task group was to develop a methodology that incorporated explicit uncertainty analysis, and specifically dedicated to wastewater plant design. So the slide you see shows the methodology proposed in the STR, and we identify several steps. I'm not going to go through them in detail. They start from defining the project objectives, propagating uncertainty, and the end result being that the generation of a metrics that quantify the risk of a specific design. So the goal is to provide the design engineers with an example of a method that quantifies the probability, for example, of a compliance of a design. Lorenzo, Bruce, and Peter will actually discuss some of the key elements of the procedure and its application in case studies. And finally, we also wanted to provide a wider perspective on what introduces risk to engineering projects and impacts decisions, such as the selection of a process or the size of a unit. So in the STR, we identified 2 key areas: the stakeholders, because when we plan, design, or operate treatment plants, various stakeholders need to take decisions at different points under uncertainty. And so this varies, of course, depending on the stakeholder. And our second big category was the project delivery method used. So that's the contractual environment that we work in. So in infrastructure procurement, the contract delivery mechanism determines how risk is allocated between among stakeholders. So depending on the way the infrastructure procurement contract is set up, risk will be allocated differently to the owner, the engineer, or the contractor. So as I've already mentioned, these and much, much more can be found in the STR. And on the slide, I have added the websites through which the printed or the ebook can be purchased. So this is all from me. We'll now introduce our next speaker, Lorenzo. I will stop sharing my screen. Lorenzo. So Lorenzo has completed his master's in environmental engineering at the University of Florence and his PhD and postdoc at Ghent. From 2010, he has worked as an independent consultant with waterways based in Italy and in Croatia. He has 23 years of experience in modeling integrated wastewater systems. He's the founder of the IWA Working Group on Modeling of Integrated Urban Water Systems and the secretary of the DOUT Group. Lorenzo.
Yeah, thank you, Lina. Hi, everyone. I'm going to start with a few key definitions for variability, risk, uncertainty, and uncertainty propagation in models. First of all, variability, which is defined as the lack of consistency or fixed pattern, and it refers to a measurable quantity that varies in time, and it can be represented by a time series. So variability is intrinsic. It cannot be reduced. For example, rainfall, you can measure it, but you cannot increase or decrease the variability. So if you have a model and you feed it with always the same time series of influent flow, you will always get the same effluent time series for ammonium, with everything else staying the same, of course. Now about risk and uncertainty. Risk is defined as the expectation of losses associated with a harmful event. For example, the risk of failure of exceeding the effluent permit. Risk is calculated as the probability of failure times the cost of failure. Probability answers the questions whether it is likely or unlikely that the event will happen. So for example, what is the probability of a design to meet the effluent standards? Probability is the expected likelihood of occurrence of an event. So at the end, uncertainty assessment and propagation are the quantification of probabilities. This means that quantifying risk means assessing uncertainty, which means quantifying probability. There are different levels of uncertainty, going from complete determinism to full indeterminacy, going through statistical uncertainty, scenario uncertainty, qualitative uncertainty, recognized ignorance, and total ignorance. We're going to have a look only at the two quantitative types of uncertainty. First, scenario uncertainty, which deals with questions like, what is going to happen at my plant in the next 30 years? What about new industries in my catchment? What about new treatment technologies available, new legal requirements to fulfill? So to these type of scenarios, I can actually maybe put numbers that I can run with my model, with separate scenarios, but I cannot really give statistical properties to those. On the other hand, statistical uncertainty refers to epistemic situations involving imperfect knowledge, imperfect or unknown information, or also a state of limited knowledge where it is impossible to exactly describe the existing state or a future outcome. So in this case, we can assign probability density function to those quantities, and we can reduce the uncertainty by more research, by more measurements. If we measure more an uncertain parameter, we can reduce this uncertainty. So how do we propagate uncertainty through our models? We do that with so-called Monte Carlo simulation, which is sampling many times the input parameter distributions. We start in the probabilistic domain with the distributions of the inputs. So we run Monte Carlo simulation, which is, as I've shown, many samples. Every sample is called a shot, which is a value for each of the input parameters. And these values are put into my deterministic model, which is run and produces discrete results. This is done many times, as I've said already. We have many time series, many results. These are summarized in the probabilistic domain by means of a statistical analysis, which will produce distributions of the results, probability distributions. And we can summarize those by means of, for example, an average or a 90th percentile. This is an example of the type of results we can get. This is a few days of ammonium effluent of a plant. And if we look at the blue line, this represents the temporal variability due to the influent variability, is the result of a single simulation. In red, we have the output uncertainty band due to the parameter uncertainty. So this is the result of the Monte Carlo simulation, and specifically here, the 95th and the 5th percentiles. And this means that I'm 90% confident that the true result will be within this band. Now, with another point of view, we can have 4 different ways to combine variability, so steady state or dynamic simulation, and uncertainty, so single or Monte Carlo simulation. So if we have a single steady state simulation, so no Monte Carlo, one simulation, we get a point estimate as a result. So we can say that ammonium effluent is 2.2 milligrams per liter. If we still use steady state simulations, but with Monte Carlo, for example, 1000 simulations, we can calculate a confidence interval, which represents uncertainty. So we can say here, for example, that I'm 90% confident that the effluent will be between 1.5 and 4.1 milligrams per liter. If we go back to a single simulation, but dynamic, and if we plot the effluent time series as a cumulative curve, we can calculate the frequency estimate. So we can say something like ammonium will be 90% of the time below 2.4 milligrams per liter. If we combine the two, so dynamic simulations summarized by cumulative curves and Monte Carlo simulations, I have the frequency and the confidence, so variability and uncertainty. And I can say, for example, that I'm 50% sure that I'm 90% of the time below 3. Or again, that I'm 95% sure that I'm 90% of the time below 4.3. So in summary, variability is something, let's say, sure, that we push it through the model and we get the frequency of compliance. On the other hand, uncertainty is about possible futures. So confidence means in how many possible futures something is happening. Thank you. That's the end of my presentation.
Thank you, Lorenzo. So we will now continue with our case studies. We'll start with Bruce. And Bruce, okay, he's getting ready. Good. Bruce Johnson is a wastewater technology senior fellow with Jacobs, located in Denver in the USA. He has been doing wastewater treatment design for over 30 years. And he has held various roles in wastewater process and simulation global as a wastewater process and simulation global technology leader. He's very active in WEF and IWA. He's a past scientific chair of WWR Mod, and he's also a founding member, as you saw, of the DOUT Group. So one thing I would like to let you know is that Bruce will unfortunately won't be able to join us for the joint discussion. So if you have any questions regarding any of the case studies, please, we will assign some time after his presentation. Please ask them now, and Bruce will answer them at the end of his presentation. Bruce.
Thanks, Lena. Can you guys see my screen and hear me okay?
Yes.
Everything is fine, Bruce. Yep.
Okay, good. Okay, thanks everyone. So I'd like to talk about our experience with applying the principles that Lena and Lorenzo have talked about so far to steady state evaluations of uncertainty analysis with a very large team of folks that helped pull these together. So as Lena and Lorenzo were talking about, when we got uncertainty in the system, we can actually start actively managing risk in the design and in our wastewater plants. We've been doing this for a long time, but it's usually been engineers using their expert knowledge about what's appropriate there, and usually it ends up being fairly conservative. So the relatively new thing in our industry is this widespread use of simulators and how we can best use them in our work to get better value out of our designs. As Lorenzo pointed out, models do not give the answer. I mean, you get one answer, but we all know that that isn't really the way it works. And there's thousands of parameters that might impact that. So will we ever get an exact answer out of a single simulation? No, we won't. The reality is always going to be different in some way. There's a saying out there, I don't have the attribution of it right now, but all models are wrong and some are useful. And we believe on that. I believe on that. So as Lorenzo pointed out, we can quantitatively evaluate the statistics of things happening at the plant. And this actually requires daylighting the risks that we've buried within those risk factors in our designs. And this allows us to manage that risk rather than doing the more typical risk avoidance approach in our designs, which can have some fairly significant cost implications. So some examples of doing this is, first of all, at Meridian, Idaho in the US, where we did a statistical re-rating of the facility. So this facility is a medium-sized plant, about 35,000 cubic meters per day. And the capacity in North America was based on kind of a standard approach of maximum 30-day loads and flows happening at the same time. We wanted to see how realistic was that? What's the actual likelihood of it? So what we did is we looked at various input parameters and we actually put statistics to them in a steady state simulation there. We've got the list that I don't need to go through, I don't think. And if you've never plotted this, this is really interesting in facilities about flow and load in there. And this graph, flow is on the X and load is on the Y axis. You can see that it's essentially a scatter plot. And there's no real relationship between flow and load in there. It's just kind of random in it. So using this statistical analysis and going forward with the plant, we were able to actually give a new rating of the facility. In this case, the original rating was about that 34,500 at that red dashed line. And as Lorenzo was pointing out, there's different ways of evaluating the risk. If we look just on the average rating capacity of it, that we're complying 50% of the time, we could actually have quite a bit more capacity because the capacity is actually defined this blue line. It's way off the axis at the high flows. But in the US, the EPA maximum month is about the 95th percentile or the red line. So in this case, the red line intersects with that 90th percentile confidence of achieving it at about 38,600 cubic meters per day. So this gave about a 12% re-rating increase at the plant, essentially for free for this utility by using this approach, and it was accepted by the local regulatory agency. Another example is at the Blue Plains plant, the large facility in Washington, D.C. in the US. The design flow of this plant is 1.4 million cubic meters per day. And we were looking at what the capacity would be to achieve a TN of less than 4 milligrams per liter out of this new facility we were putting at the end. And it was unclear if, because we were using all the volume we could there in a very limited site, it was unclear if we were able to achieve that within the available area. So similar to Meridian, we did a whole bunch of new simulations, about 3,000. And we combined those together in typical months in seasonal and then into year, because there is a yearly permit there. And we actually looked at TIN as our criteria for this. And we had a number of inputs into there, a number of kind of conventional ones, temperature, flows and loads and everything. But I'll point out, we also put in some, I'll call them more operational uncertainties. Is a nitrification tank out of service, denite tank out of service? Is the methanol being delivered on time at the plant? And we could quantify this in an uncertainty type basis to develop the likelihood of the plant achieving the goals. And so what we found out when we ran through this uncertainty analysis is that we got very good compliance. Almost all the values were less than our target 1 TIN, which we thought we needed to hit the 4 TN. But we did have a bimodal criteria here where we got some higher numbers here at the end. And all of these results were really a result of automatic control and not having operator intervention, which could do this. And so we determined out of this that there was equivalent to about 1 year and 27 years of operations that it might exceed if there's not even any operator intervention. So it gave DC Water great confidence in that this facility was able to meet their goals for their plant. Now, the last one was a Durham plant in Tigard, Oregon, in the US. Adrian Minetti, who's now with Clean Water Services, did this work. And in this, this plant was looking at needing to achieve nitrification in the winter time, which they had not needed to do before. And they wanted to know how they needed to run their plant to achieve this goal during the winter time. So they have a very complex permit in this plant, and their effluent ammonia in the winter time would be a function of both the river flows and the temperatures going on there. And so what we did is we used the EPA's nitrification safety factor in a very simple spreadsheet, actually, to look at the impacts of sludge age, river flow, influent temperature, the historical patterns, the nitrifier maximum specific growth rate, decays, oxygen, and the various probability of those functions. And what we found in there was that if they targeted 1.3 nitrification safety factor, or about an 8-day during the season, that covered them to achieve their nitrification goals for almost all conditions over the winter time. It didn't quite meet the 99th percentile reliability, but it felt like this was a good point to hit in the plant. And what this meant to them is they did not have to, it greatly reduced the need to expand the plant and allowed them both to extend the timing of an expansion and the amount of expansion they needed at the plant, which had some significant cost implications, reduced cost implications through the plant. And just to show you that this has been used at a bunch of other facilities all around North America to help various utilities identify either what their risks are or opportunities were to achieve cost savings by using uncertainty analysis. So the use of uncertainty analysis in wastewater treatment has been shown in the case studies and these others to provide both quantitative risk data and the associated cost savings with it. utilities can now participate in that risk for their facility and not just rely on whatever the engineer or designer has to say about the risks there. It allows for more informed decisions in the design, construction, and operation of any facility. And it can be as simple as applying Monte Carlo analysis to basic design equations, as we did in the clean water services, or we can do whole plant simulator runs, as we did in the other two facilities. And this use of uncertainty analysis is really a logical step to provide data to make more informed decisions in our designs and approaches. And as Lena said, I'm not going to be around, so I'm going to try and answer a couple of questions here. Lena, I haven't been able to look at the chat too much. Is there anything I need to specifically answer in there, or if there's any other questions?
So we do have a question, but I think this is more of a generic question, which we might answer in the discussion a little bit later. I have a question specifically for you. Before I pose my question, though, I would like to just make sure that everybody's aware of the fact that if you have questions, just use the Q&A window, because the chat is not available to you. So my my question to you is how easy was it for you to convince the utilities to use this approach, and which was a change to the conventional approach of design?
It's a great question, because this type of discussion actually requires a significant mental shift in the utilities to go from a risk avoidance to a risk management perspective. Usually the deciding piece in it that made it really attractive to them is the significant cost savings they could do by doing this. And so it wasn't really until we got to that point of showing the cost savings that they got all on board with it. Until then, it was very uncertain about, if they thought this would be useful or not. They were trusting us to say that this will give benefit for them. In the case of Meridian, we actually brought the regulator with us along on the whole path as we were developing and proposing and working through this to make sure they understood and accepted what we were doing. And that seemed to work pretty well. And pretty much all the utilities that have been involved in this has found good benefits with it if they can make the mind shift between that risk avoidance and risk management type of a thought process.
Thank you, Bruce. I think this has stimulated people starting adding questions here. I have another one from you. How do you determine which sources of uncertainty to consider in your simulations?
That is, I think the formal term is expert opinion in there, and it's basically people knowing what there are two ways. You can do a sensitivity analysis where a lot of these Monte Carlo tools will help tell you what the most sensitive parameters are into your results. Or you can do you can use your expert opinion. If people know modeling well, many of us on this call know what those most sensitive parameters normally are. And so they're the ones that we use, like on DC water. We used a number of different ones that we knew were highly variable. And then we talked with the operations staff about what the operational uncertainties were at the plant to come up with these. So there is a lot of expert opinion involved in that, but there are also quantitative ways through sensitivity analysis to do model-based type parameter determinations.
Thank you, Bruce. So I think maybe one more question for you. So when you were looking at the evaluation for nitrification in one of your case studies, what did you use as inputs for the model? Did you vary the tank volumes for different simulations? How do you include, maybe you can discuss a little bit how you did this evaluation for the nitrification capacity.
Yes, so in this case, we kept the existing system that they had, and we wanted to find what the existing system needed to run at to work okay in the plant. And so based on that, we didn't vary tank temperature or tank volumes or anything like that. So we did an historical analysis and fit probability distribution functions to flows and influent temperatures, and then also correlated them together because those two are actually correlated, where as river flow goes up, influent temperature tends to go down at the plant. And then we put in expert opinion on the possible different nitrifier growth rates, decays, and KOAs in there. And we were able to combine that into a single Monte Carlo simulation with us in that simple spreadsheet of the nitrification safety factor calculation, and then compared that result against the actual performance of the plant. In this graph here, you can see that the 1.3 started getting anything above that value got pretty reliable nitrification out of the plant with the river. So that is how we did that.
Thank you, Bruce. I think we're going to stop the questions here. There's a couple more addressed to you, Bruce. Maybe while before you leave, you might have the chance to maybe open the Q&A box and type in your answers. If you don't have the chance, then we will make sure that they are answered later on. So I will now introduce our next speaker, Peter van Rolligem. Peter holds the Canada Research Chair on Water Quality Modeling at Université Laval in Quebec City in Canada. He is the director of the Model Law Research Team, which focuses on modeling, monitoring, and control of water systems. He is extremely active within IWA and WEF. And he's also the co-chair of the Design and Operations Uncertainty Task Group. Peter. Unmute yourself.
And turn on your video.
Hello. I think we're just going to move this away. Good to not hear you, but at least get in touch with you. Good afternoon, good evening, good morning. What I will do is to present work that we did on within the DOUT activities to develop a procedure to work with dynamics in the system. So you've seen a few examples on steady state. Bruce already mentioned that they also apply this methodology for dynamic cases. And I would just like to thank Talabijat and Mazur that did his PhD in the group with Lena Belia as co-director as part of the DOUT work. So what you will see is the procedure that we developed in this PhD study, where a lot of information was, of course, coming from the whole DOUT team. So we know that WRFs are dynamic systems. And if you look at steady state design, then we use constant values for design inputs. So even though reality is this, in steady state, we may take a value, an average value, or some peak value, or some percentile value as information, run that through design guidelines that use steady state equations, you've seen this already, and then come up with designs. And then we may check with dynamic simulation how this will all work under special situations, overload situation, wet weather events, what have you, using the parameters that came from this steady state design. You've seen this graph as well. So you take a number of elements of steady state design, you run it through the process-based equations, some of them with empirical equations, some experience-based rules, and you come up with the treatment plan's dimensions. So the objectives of the work that was already happening, but that we wanted to formalize, was that we wanted to explicitly consider influence variability and model parameter uncertainty. We wanted to, or we used the term probability of non-compliance to express the uncertainty that might come with the design objectives that we try to reach. We don't see this as a replacement of the conventional design approach, more as a complement, and it should be applicable to actual design projects. So we try to add something to what is currently happening. Basically, my presentation is about this proposed design methodology. It consists of 3 main steps. You do a pre-design using classic methods, steady state pre-design with different levels of safety. You're going to analyze those pre-designs and do a preliminary evaluation of how they look, how they work, how they perform. And then you go into the detailed dynamic simulations to assess the probability of non-compliance. So the reason why we do the screening, these 2 first steps, is basically to reduce the number of things you have to evaluate with compute-intensive dynamic simulations. So you will create inputs that are the range of values you expect, uncertainty bounds, and out will come a curve that you've seen already, performance of the design in terms of probability of non-compliance, given a certain effluent standard. This was applied and tested on the Eindhoven treatment facility, which is well known for a place where many things are being tried in terms of nutrient removal, modeling aspects, CFD, also uncertainty analysis was applied to that plant. And Stefan Weyers, who was member of the DOUT Group, allowed us to work with detailed information that would be available to designers. Just to tell you what the effluent requirements are for this plant, total nitrogen is 10 milligram per liter on an annual basis. Ammonia is 2 on a daily basis. BOD 5 is 20 on a daily basis. COD 125 on a daily basis, and suspended solids is 30. We will focus on the nitrogen part in this application. I'll first go through the first 2 steps. This is really a short presentation. There's extensive presentations about this methodology if you would like to hear about this, and then we'll go to the PONC quantification. So rather than doing this, we're going to do this. We're going to evaluate a number of possibilities, potential designs, by looking at the uncertainty around influent constituents, by looking at different safety factors, by looking at some of the parameters that we use in our design models, operational parameters. Of course, the effluent standard, we don't play with that. And then outcomes, of course, not one design, but multiple designs. And we look at here the 4 variables that we looked in this example of total volume, anaerobic volume for the phosphorus removal, the depth of the final settling tank, and the area of the final settling tank. What comes out of this are hundreds of design values. So I run and run and run Monte Carlo runs with randomly selected points in these gray boxes, and out come these gray box on the right, which gives us all these dimensions. And it becomes a cloud because we have 4 dimensions here. So the 4 design variables we have. And what you see, the red dots are basically selected ones that we select because we want to cover the gray dot space. And basically, these are the ones that we're going to analyze in detail. So you see on the diagonal, you see the distribution of these 4 outputs of the design. So volumes, areas, depth of subsystems. And you see that some of these are correlated, although the correlation is really small. So the design variables are not very depending on each other. Now, what we're going to do now is the dynamic simulation, calculating the probability of non-compliance for each of these designs, these red dots, which have particular volumes and areas. And what is done here is that we will look at the model parameters, and we have information from literature, from our experience on how uncertain they are. And people know that yield coefficients, for instance, are more certain than affinity constant or growth rates. These are one part. These are the process model parameters. And then you have the big uncertainties that come with, and variabilities that come with influent time series, flows, concentrations. The bottom one there is the temperature. You see, these profiles of temperature, because we're going to do in this procedure a whole year evaluation. These sources of information will randomly be selected. So we'll have random selection of model parameters. We'll have random creation of influent time series that will cover the variability and uncertainty that we can expect in real treatment plants. And we'll run that through our model that is a pre-configured design with certain volumes. And we'll see how these different designs will operate. So we get time series out of them, of ammonia, for instance, in this case. And you see that the winter is a bit more difficult than the summer to nitrify completely. We will transform this into a cumulative distribution function, which basically tells you what percentage of the data have an ammonia concentration.
Don't worry, Peter, we'll be back. This is something that he warned us about. It could happen. He might freeze for a couple of seconds, but he'll be back. So just hold on. We hope.
So I lost my connection apparently. Hello.
Yes, we can
You're back
hear you.
online, Peter. Yes.
Okay,
Start
that's
sharing again.
sorry for that. It happens here in EAWAG where I am sometimes that we have a glitch in the ED-ROM connection. Sorry for that. I hope I didn't. So I'll just go back to the influence generator. I think I got there, correct?
Go back one more slide.
Yeah,
Okay.
Peter, you have to go from the CDF to PDF, then to the
Okay.
notes.
Okay. Thank you. I don't know when I stopped. So what we have done is we have time series for each of these runs, which will be different, of course. The ammonia will be higher or lower depending on the parameters that you have, or the influent loading, or the temperature profile you put in. Each of these will be transformed in its concentration distribution function. So it will be left or right, or maybe higher slope or lower slope. And then we calculate from these curves the probability of non-compliance. So it's 90% sure that we will not be able to reach the 2 milligram per liter limit in the example that we have. One of the important parts of the whole running of dynamic simulations compared to steady state simulations is to find really a reasonable, realistic time series and multiple time series. We want to run this not for 1 year, but every year will be different in the future of this plant. So we want to make sure that we covered it enough. So what we've spent quite some time on in the project was to create an influence generator, and there's multiple ones in the field. What we wanted to make sure is that it's quite realistic and that it can cover meteorological information, because we have combined sewers in many cases, and it should also cover uncertainty and properties of the generation of pollution in the city or in the runoff. We use for this city drain, which is an existing model that comes from the sewer system modelers, where it allowed us to propagate nicely rainfall, also doing runoff accumulation wash off in the catchment. And then we have, of course, a dry weather part. And we have the Muskingum routing that allows you to do hydrological propagation. And we have made a rainfall generator, which is based on Markov chains, that will generate on the basis of historical data, will create new time series of rain that come out. And this gives us a tool that allows us to prepare influent time series for hundreds of years, let's say, all different. So once you have this influent profile, you can basically put it through the wastewater treatment facility model that we have, and you will play around then with properties in this process, properties of settling, growth, etc. And the designs will be placed on, in our case, the 4 elements that we look at. I'll just give you now a few results to illustrate what comes out, and I will present it in multiple ways. So we have here 5 alternatives, alternative 1, 2, 3, 4, and 5. And for each of them, we have this calculation of the ammonia concentration, cumulative distribution. And you see that there's 3 lines on this. The worst case is basically the concentration cumulative distribution that we get for the time series of 1 year with the worst case parameters. Worst case parameters would mean the lowest levels of nitrification capacity for this one. The nominal one is what we call defaults, that you all know from the models that we typically use, and mixed is a kind of average of all the Monte Carlo simulations we've done. And in this case, they're pretty close to each other. What you get out of this, and for alternative 3, for instance, is that in the worst case, the red line here, the limit is 2 milligrams. We can expect that 29 days in a whole year, you would be above the limit. Whereas if you look at the other parameters, we talk about 3 to 4 days. So it's much closer to the top here. There's a few days where you might go over the limit. And then the question is, do you accept this or not? That's the design question. Just looking at what the real plant is that was already built before this methodology was applied. The real design is in between alternative 3 and 4. So this is the design that exists in Eindhoven. These are the numbers that came out of the designs 3 and 4, and you see that it's pretty close to these. Let's look at some other ways of presenting this. What you see here is for 3 parameter sets. So this is the average of all the Monte Carlos. These are the default parameters, and this is the worst case parameters. Notice that the number of non-compliance days is given here, and the 3 graphs are having different values. So there's 90 days, 45 days, 180 days. And you see that, of course, that the best plant, the biggest plant, has the least non-compliance days, logically, compared to the alternative 1, which is a small plant, which is hardly able to do a good job. So this is a type of information that you can also, it's reorganizing the data in a way that gives you this information. The last graph I want to show is this one, where we basically look now at the volume. This is one of the total volume of the system. And you see how if by increasing the total volume, the probability of non-compliance is going down significantly. And again, depending on the parameter set, the worst case parameter set will of course give more probability of non-compliance. And this is the information you can give then to a design engineer to basically come up with designs and explain the risk of non-compliance. And at some point, a decision will be made of what's acceptable. So in summary, the work that has been done by Mansour has allowed to develop a design method that is based on explicit characterization of variability and uncertainty. One of the contributions that was important to make this all work is to get an influence generator that can generate those variabilities and uncertainties and preserve the observed statistics in data. I think we have developed a rigorous calculation method of the probability of non-compliance, PONC, and we've applied this to an actual case study. And I think I would like to thank some financial support for these studies, and Mark, Christina, and Mansour for their creative moments to come up to this methodology. I think that's it for me.
Thank you. We will now move to Mark's presentation. Mark Neumann is the IG Basque research professor at the Basque Center for Climate Change in Bilbao, where he coordinates the research line on adaptation. He holds a PhD in environmental engineering from ETH Zurich, and he was a postdoctoral researcher before joining BC3 at IRVAG and Model Law in Canada with Peter. He has extensive research experience on the mathematical modeling of urban water systems with the focus on the treatment of uncertainty. Mark.
Thank you, Lina. And I'm going to give the thank you back to Peter, who just ended by thanking me. Thank you, Peter and Lina. I think this, if I go to my next slide, just a minute. I want to show some perspective now, and the thank you is related to this fact here in the second bullet point on the co-production, which in academia at the moment is quite a fancy buzzword. And what we realize here that this has been with this the end product coming out at the end, the co-production between academia and practice. On the one hand, led by the collaboration of Peter van Rolligem at Université Laval and Lina Belia at Prime Model. And on the other hand, through the large amount of workshops that took place, especially in the first years of the task group, workshops at mainly IWA and at WEF conferences, where academics and practitioners got together to try and frame these issues. And I think one of the things that the STR especially highlights is that it is necessary to unpack these issues of treating uncertainty with respect to the stages of design or planning in practice. So the STR has quite a bit of information on how to structure the discussion of uncertainty across the project phases, from regulatory planning, design, operations, across the different stakeholders, the regulators, the utilities, the owners, the consulting engineers, and very importantly, the different project delivery methods The SDR itself has focused mainly, and that was the objective from the beginning, on quantitative approaches for planning and design. Also, to some extent, on optimization and operations. And this opportunity of co-production has been a source of sparking new ideas, further academic investigations, and given the opportunity of testing some of these methods in practice, as we saw in the presentation by Bruce. Now I will just try to zoom out a little bit and touch on some of the broader issues that are implied in this work. One, these are issues that came up in these workshops. And the first one is related to transparency and explicitness. So that relates to the issue of making, when using this uncertainty analysis in the modeling context for design, to make very explicit the different assumptions that were taken at each step in the process, and to be transparent about that as well. Then the second point that was deemed as very important is, as we're moving forward, we would really be interested in knowing, well, how well are such designs that are done probabilistically? And what this really requires then, and one of the questions I saw in the chat was referring to that, to the data storage. So this requires a high resolution continuous monitoring over a long-term horizon over several years to understand which kind of non-compliance events that Peter was referring to are captured with the models and which ones are not, in view of also upgrading these design procedures. And this also would then allow ex post assessments of designs. So to see how, as reality unfolds, how they compare to the design assumptions that were made initially. Then a third point that was very important that kept coming up is the importance of gaining a better appreciation, and when possible also quantification, of how the benefits, costs, and risks are spread across the different agents in these projects. Then, for looking into the future, which in some way has already happened, as this process started nearly 14 years ago, is two main aspects were touched upon. One was related to the model and simulator evolution, and related to that, the applied mathematics, let's say. And the other one related to the more of the social aspects and economic aspects. So just briefly in the model and simulator evolution is some of the uncertainties that we started working on at the beginning start to become resolved by having high resolution, be it in time, where we start capturing the actual dynamics, or in space through the use of computational fluid dynamics. Then the fact also of using increased use of integrated models is moving us away a little bit from the pure design of unit processes to the actual design of integrated systems. And then fourthly here, as the computational power gets stronger across time, this allows us to use more powerful statistical techniques. Then in the integration more on the economics side, what we appreciated in this work is that in the curve that Lina showed at the beginning, where we had in some way the degrees of freedom as a function of the project stage, that a lot of the central uncertainties are right at the beginning, so at the regulation or at the planning, and that we're still lacking a more structured use of foresighting or structured scenario analysis type of techniques to address this. And also our effluent requirements are becoming more complex. So we're typically not designing just to 2 or 3 concentration limits, but we are getting more and more objectives that we're needing to comply with on a life cycle, from a life cycle perspective. And then these last 2 points, they touch again to this need of economic evaluation of the economic part of the evaluation of the benefits, cost, and risk, where Bruce also showed us in one of his examples how that then also starts to become a motivating or even a necessary factor to start taking this explicit view of dealing with uncertainty. Then very briefly, and this is just touching in some way the work that we did here, is that there are also other ways of trying to think of dealing with uncertainty, which beyond the actual quantification. And I have just listed a few here, which I will not go into detail, as we're going to go into the questions and answers session very shortly. But you can imagine here, just as one example, as decentralization, which might substantially reduce uncertainties with regard to the planning phase. So you're not, if in the extreme case you have a 1 plant per building, 1 treatment plant per building scenario, then the uncertainty about the future size of the city, which is connected to a single central treatment plant, becomes smaller. But maybe uncertainties regarding operations become larger. So we have other options here also to address uncertainty, also moving into robustness and into uncertainties related to reliability in operations. And then maybe more holistically into resilience, into understanding how wastewater treatment plants are interconnected with other aspects of urban public services, or with the wider issues in a catchment or in a river basin. So with this, I'd just like to remind you again that you can find the scientific and technical report number 21, it is, through the IWA publishing homepages. And with this, we'll move to the question and answer sessions. Okay. I will just start with the first one that I have on my screen. Did the group consider a possible difference between capital project risk and operation performance risk? That is, a capital project happens once, so the concept of risk equals cost, or equals probability times cost, may not really result in an expected value. In production, perhaps like operation, the results are based on many trials, so the actual cost can be close to the expected value calculated by the risk-cost equation. This maybe needs a bit of unpacking. I just probably chose the most difficult question we have in the list.
It's a very good point, actually. And of course, in our work, we didn't explicitly tackle it that way.
Well, it's already also a paradigm shift if you start looking at total cost, that you don't consider only the capital cost but also operation cost and what you're going to design for. I think this.
Well, this heavily depends also on what we mentioned about the contracting type. So if we have a design, build, operate, transfer, or design build, this is strongly related to this and to what I mentioned on the spreading of risks, benefits, and costs across the different stakeholders.
So what we did in Mansour's work was look at capital cost and operating cost, but not in a great detail. So you could run simulations over a year and then look at maybe the loading that would come in 20 years, doing some expectations coming in, and see how that would evolve. And then depending on the design you'll have, you look at the total cost that may be different depending on the scenario you're running. So the whole difficulty is what you do with the efficiency of a plant in 20 years when there's new developments. How do you handle that in terms of total cost calculation? How do you make this acceptable to make a design choice that looks at possible futures that are really uncertain in terms of what can develop in the future? But I think it's a very good question that is especially important because you look at this conflict between investing a lot in the beginning and then living with low operating costs, or saying, okay, I will reduce my capital cost even though I know that operating costs will be higher. These are interesting design choices that have not only to do with uncertainty. I think it's just the whole design procedure is in question there.
And I think that there's also a further discussion along the lines of how companies do evaluate the risk, whether especially with looking at capital risk, where they have risk registers, and because capital risk involves a lot of financial risk, so there's a financial department that will be involved. It's not just the design aspect of it. So that is it kind of opens up a wider range of risks involved. And
especially who is going to carry the risk. Depending on the system that you're working with, it might be the city that takes most of the risk, or it might be the company that builds it that is getting most of the risk. So these are interesting subjects of discussion, I'm sure. No answer, no. I don't think we can say.
It's relating back to the contract types again, I think, and that is where, just from my point of view, entering as an academic, that was quite important. Where we'd previously been doing these uncertainty sensitivity analysis starting from the model, but of course you can. If you're working with a team that is developing a bid, you're going to see that these contract types are fundamental in how in assuming which stakeholders are going to be taking on the risk. There's another question related to, I think, from Timothy Holloway that could be related to this as well. Could anonymized treatment plant data sharing be used to understand uncertainty? Would this accelerate the understanding of the actual uncertainty occurring in a live or in a real treatment plant? I think that would be a very interesting initiative, maybe for a new task group. So to collect anonymized treatment plant across a large number of treatment plants, and to improve that understanding, maybe also through the tagging of non-compliance events. What are they related to? Could they be captured? Would they be captured in the probabilistic design, or are they outside of the model capacity?
So with Lorenzo, we did a long time ago a kind of like a post-appraisal of a design, actually for the Eindhoven treatment plant, I think this is a very valuable procedure to go through. I'm not quite sure how easy what you're describing, Mark, is a huge effort, but very, very valuable, of course.
I think that the variability assessment is probably easier to find out how variable things are. The uncertainty, I think you need to have a bit more data treatment, and it should be standardized somehow to make sure that you can express or exchange uncertainties in a certain way, because the way that you do it is giving different results. I would say variability is probably easier to do than the uncertainty part.
The other thing I was going to say, that this is a question, it kind of opens up the topic of how do you actually move these methods to become more common in practice. We had a couple of comments which were answered, I think some of them by Bruce, and that is another very important question. It involves not only how do you transmit the confidence to the treatment plant owners, the confidence that these methods will give them additional answers and benefits, and also also how do you involve more researchers as well? So I think it's a very important kind of element of this whole range of questions along those lines.
Okay. From Oscar Samuelson, if I understand correctly, model simulations were mainly used for validating design and not for the actual design. Could you elaborate a bit more on this, how this choice was made? And maybe a follow-up question, what would need to change to allow replacement of design guidelines with model simulations?
I think Bruce would be the person.
Yeah, I think I would also think, I think Bruce showed some examples of actual designs they were doing.
And they were not validating designs. I think they really made designs that convinced utilities to go with them in this process. So I think that's on a dynamic case. The ones that he mentioned, I think, is very similar. He used dynamic simulations to come up with a design. And I think he made also a comment. I think we felt it during the discussion that we had as well. It's mainly that the people in utilities and decision makers are opening up for this type of approach and dare to use it and feel confident this is making that designs are better made, maybe saving money, but also just being better made because they give you are more certain of what's going to happen, even though you do uncertainty analysis and maybe it's about confidence building of what you're going to do, what you're going to get.
Yeah, but
I think
it really
Oscar's, I'm sorry, go ahead,
yeah,
Lorenzo.
It really depends on the country and company, because in some countries they require to start with some guideline and then you can use a dynamic model to validate. And in some companies, they have they are used to start with their own steady state models, and then they validate with a dynamic model. So it really depends on the combination of country and company culture.
And what I was going to add is that that's exactly the reason why I think to the second bullet that Oscar has, that was one of the reasons why Mansour's work, if you see the way that, when Peter was presenting it, it starts off by preliminary designs based on current guidelines. So you start off with what is the norm, what is accepted, or what is the rule, and then you add on the analysis through a steady state or a dynamic model, which allows you to get so much more information out. And this also helps, I think, the transition.
Okay. Then we have a question, how can you include climate change potential impacts for the risk uncertainty quantification?
The way that I see it is that I would consider it on the scenarios that you have from climate change that are existing. And Mark, you should answer this because you're in the climate change group in Bilbao, right? But I think there's potential. We've done already some studies on what we'd expect in terms of rain intensities to go up, more frequent rains, more long dry periods, temperatures going up. So there's a number of things that we can directly include in our scenarios that we run. And this way, think about what might happen in 20 or 30 years as a plant is still standing there as it's just been implemented now. So I think you can do quite some work on that. But Mark, I'm sure you know much more how to do it.
Maybe to add to that, I mean, I think the main way to go is through the scenarios, especially as you have these emission pathway scenarios, and for each emission pathway scenario, you have a different intensity of climate change. And then you would have that as scenarios of temperature change. So maybe the change of the wastewater temperature itself, and then of mainly rainfall variability patterns. In addition, I think here it's maybe important to say as well in the experience that we've done looking backwards in time. So how has adaptation happened in the past to disruption? Especially for wastewater treatment plants, if we're thinking a 20-year time horizon, there's probably a lot of other drivers or forces that have a bigger signal than climate change. So changes in behavior in water use, in industries moving away in the catchment, also new regulations coming in, like on new chemicals or nanoparticles and so on. So
but these are probably less predictable now, because
yeah,
20 years ago,
less
we would have
predictable, but that probably have a bigger signal in the 20-year.
Sure.
Of course, in a 100-year perspective, it changes a lot, and then the climate change signal becomes a dominant force. Okay.
Well,
Yeah.
okay, my friends, I think we are running, we're in minute 85 now. I think it's time to think about concluding. We have it's great to see that everybody is still online, or basically everybody is still online, even though we have continued a bit over time. But I just want to, before we say goodbye, I just want to thank, of course, all the 5 presenters for a great show. And I want to remind everybody who's listening that we will have a short summer holiday now, but we plan to come back with another MIA modeling webinar on some interesting topic in September 2022. And I want to thank the various members of the management committee of the MIA specialist group for coordinating and arranging large parts of this webinar, none mentioned and none forgotten. And please also realize that if you have ideas of setting up a webinar on some modeling topic, then feel free to contact me or anybody else on the management committee of the MIA group, and we will try to make it happen. We will try to fit you into the agenda, and you can have a type of webinar as you have just been listening to. So, and finally, if you are not an IWA member, then I am kind of obliged to say that please consider to become one, so that you can enjoy all the benefits of what that membership brings to you. And with that, I want to say thank you again for everybody, and hope to see you in Copenhagen, and hope to have you here on the screen for our next webinar in September. Bye-bye.